Good evening. Tonight I will show you how to create the simplest conceivable PCI device driver for Windows NT 4.0. Let me preface this with full disclosure that the code in this video is entirely generated by ChatGPT. I've never written a driver before, and while it's something I'd been interested in trying for a while, I wouldn't even have known where to start. Also, the driver is so basic that it's hard not to have it generated in full, because by the time you've asked about the few function calls you need, you basically have the entire driver. Still, if knowing that this device driver is literal AI slop turns you off, I don't blame you. Even so, I figured it might be interesting to explain what the AI-generated code does, and to see the build process for a device driver on such an old OS. Also, there is no YouTube video on NT 4.0 driver development yet, so at least there is a bar now, low as it may be. Anyways, now that we have established that, let me explain the motivation behind this video. You can skip to the appropriate chapter if you don't care. You see, I wanted to use AC97 audio in a Windows NT 4.0 VirtualBox VM. Now, Realtek's AC97 drivers for NT 4.0 do not seem to recognize VirtualBox's sound controller. However, there is a VIA driver on the retro web which does at least recognize the sound controller and show the volume control. Unfortunately, however, there is still no audio to be heard. Some ChatGPT-aided experimenting led me to inspect the PCI registers of the sound chip using an old shareware program called PCI Tree. Now, you can't launch it just like that, because you first need to copy the file hlp.sys to C WinNT system32 drivers. Let's switch to details view. After that, you can launch PCI Tree. Being a shareware program, it of course asks you to register. Now, firstly, we need to find our AC97 controller in the list on the left. We can scroll to the side a bit and look for the term AC97. And we should see it here. So AC97 is mentioned on device 5. If you know more about PCI registers than I did when I poked around, then you know that this address contains the PCI command register, as indicated by the CMD here, as its lower word. You may also know that bit 2 of this command register enables bus mastering, which is necessary for direct memory access. DMA sounds kind of useful for a sound card, but you may notice that bit 2 is cleared. PCI Tree can also edit registers, so one can set the lower nibble of the lower byte of this command register word to 5, thereby setting bit 2. We can then click the Write Config Register button to write this value back. If we now try playing a sound, it works. Unfortunately, this change does not persist across even a warm reboot. So you would have to manually set the command register again after every boot. Brace yourselves for some loud, unpleasant static that I will hopefully remember to attenuate in post. It seems like this driver was probably not meant for VirtualBox's exact model of sound controller, but we will see shortly that it can be made to work. Now, one approach I tried was patching the driver to support VirtualBox's AC97 controller's device ID, but unfortunately that was unsuccessful. Now, another solution is to just write our own driver, which sets the PCI command register at boot up. Indeed, such a driver does not look very complicated at all, even for a novice, so that's what this video is about. As a prerequisite, one needs to install the Windows NT 4.0 driver development kit. It can be acquired and simply installs from CD-ROM like any other program. The DDK, in turn, requires the Windows SDK, which can be acquired and installed in the same way. You will need to insert your Windows NT 4.0 installation CD-ROM when the SDK setup prompts you. Once the DDK and SDK are installed, we can begin writing the driver. I will be using Visual C++ 4.1 for this, but you can use any text editor. We will be compiling it using external tools. Anyways, let's now create a new file. The first thing we'll do is click Save and navigate to the DDK folder on the hard drive root. In my admittedly limited experience, the source files must be in a subfolder of the DDK folder. I did not manage to put them at the hard drive root and access them using the DDK. So we'll create a new folder in the C:/DDK folder and call it AC97 fix. And then in there, we will save our file ac97fix.c. Okay, now for actually writing the driver. The first thing we'll do is we will include the header file entity_ddk.h. Then we will define a few macros. Define bus number, so our device was on bus 0, so we will define our bus number as 0. Then the PCI device ID is hex 2415. Hex 2415. The PCI vendor ID we're looking for is hex 8086. Fun fact, that's Intel, and yes, that is apparently a reference to the Intel 8086 processor. The next thing we'll do is we will define a structure called PCI ID, and said structure will contain two fields. It will contain a 16-bit field for the vendor ID and a 16-bit field for the device ID. We will use this later to look at each PCI device on the bus and check its actual PCI device and vendor ID against the one we're looking for. Then comes the signature of what is basically our main function. It has a return type of NT_status and is called driver entry. Now let me just quickly set up the function block. Also add a trailing new line because sometimes some programs require that. Right, now this function has two parameters. It has a pointer to driver object, which is just called driver object, and it has a pointer to Unicode string, which is called registry path. Now, these parameters won't be used by our driver, but of course they still need to be there. The next thing we'll have to do is we need to define all the variables used in this function at the very start, because this is C89, and there you can't just define variables anywhere, you need to define them at the start of a block. So the first thing we'll define is we will instantiate our PCI ID struct as ID. We will create a ulong, so a 32-bit number, which will be the device number. Then we will instantiate a PCI slot number struct called slot number and also initialize it to 0. More on this in a second. And then we will define a ushort, so a 16-bit unsigned value command register, which, as you might guess, will be where we manipulate our command register. To better understand the PCI slot number struct, let us examine PCI tree again. You can see here that PCI devices are indexed using three numbers. The bus number, which in our case is always 0, the device number, which is a 5-bit integer ranging from 0 through 31, and the function number, which is a 3-bit integer ranging from 0 through 7. You may notice that there is no slot number here. Apparently, the device and function number together with the 24-bit reserved partition constitute a 32-bit slot number. To represent this, the driver API contains a struct PCI slot number whose only member is a union called U. We can basically ignore the outer struct here. It most likely exists so that the PCI slot number data structure remains extensible if we ever need to store additional data outside of the union. The union contains another struct called bits. The bits struct contains the PCI index fields we just discussed and has a size of 32 bits. The union also contains an unsigned long field as ulong, whose size also happens to be 32 bits. Because U is a union, all of its members have to share the memory required for the largest single member. As the union members are 32 bits each, the entire union only occupies 32 bits. Because bits and as ulong occupy the same memory, if you change the fields of bits, then you also automatically change the bits of as ulong. As ulong is basically just another view for bits. This construction lets you use bits to access individual sections of this 32-bit value by their semantic meaning, which makes the code more readable. Then, once you have set the fields, you can copy the entire 32-bit contents as a single number, which is more generic when interfacing with libraries that expect to receive just a 32-bit number. Okay, now let's continue entering our code. The first thing we need to do when we run the driver is find our AC97 controller, because it may not always be device 5 on bus 0. So, to do that, we will have a for loop with device number as the loop variable. We will initialize it to 0, and it can go from 0 through 31, so it has to remain smaller than 32. And of course, it must be incremented. Now, the first thing we have to do is set the device number subsection of our slot number to the current device number. Then we call a function called hal get bus data by offset. HAL is the hardware abstraction layer, and well, get bus data by offset does exactly what it says on the tin. It gets data from the specified bus at the specified offset. Now, this function is actually a bit old-fashioned, according, at least I read that in passing the documentation. There are better approaches that are recommended for modern drivers, but this is NT 4.0, so we don't have to worry about that, I don't think. If one does use HAL get bus data by offset, then the only non-deprecated bus data type is PCI configuration, which, strangely, despite being a library-defined constant, is not spelled in fully capitalized snake case. Okay. So after the bus data type, we will add the bus number, which in this case we've defined as a macro. Then we will specify the slot number, so slot no.u.asUlong. Then we need to specify an output buffer, and in this case, that's what our PCI ID struct is for, because we want to read the vendor and device ID. So we'll specify a point. We'll pass in the address of the buffer. Now, the device ID and vendor ID is right at offset 00, so we can just specify that offset, and then we need to specify the size of our buffer, which we can do using the size of operator. Fun fact, you often see size of used with parentheses like this, and that's not wrong, but it's not strictly necessary because size of is not a function, it's an operator, so you don't actually need that. So what this function then does is it talks to the PCI bus, and for every iteration of the loop, it looks at a different device. retrieves that device's device and vendor ID. So DID is device ID, VID is vendor ID, and saves it into our ID struct, which contains it as nicely accessible fields. Then all we need to do is to say if id.vendor_id equals vendor ID and id.device ID equals device ID, break out of the loop. Now, of course, that doesn't guarantee that we actually find the device because it might just not be present. And so, in that case, we still need to do another check of the same type. So we need to check, did we actually find it? And so what we do here is we simply take this if statement, but this time, if we did not find it, we want to return status unsuccessful. So we want to return with an error. And then, of course, we now need to invert the check because this checks, is it the correct device? If we want to check, is it not the correct device, we can use De Morgan's laws. So equals becomes not equals. And then the AND becomes an OR. So if either the vendor ID or the device ID of the current vendor ID, which would be the last one we had in the loop, does not match what we're looking for, then apparently the device is nowhere to be found, at least not on bus 0. After that, at this point now we know that if we get here, we have found our AC97 controller. So now for the meat and potatoes of this. Now, firstly, we have to set the function number that we want to look at to 0. Technically, I guess this shouldn't be necessary because we initialize the entire PCI slot number to all zeros and only ever change the device number in the loop, but I guess this at least demonstrates intent. So then, now, what we do is we will set the command register appropriately by, once again, calling HAL get bus data by offset. Except this time, the offset changes. So it's still a PCI configuration, it's still bus 0, the slot number remains the same. Perhaps it should also be mentioned that, of course, the slot number already contains the appropriate device ID because we would have broken out of the loop if we found the correct device, and if we did not find the correct device, we would have ended the driver here, and so at this point the slot number is already set to the correct device ID. So what we now need to get is we now need to get the actual value of the command register. So instead of the address of ID, we pass in the address of the command register. We also have to update the size of parameter to specify the size of the command register, and the command register is now at offset hex 04 right here. So we also need to change that. Right, now we've got the command register. Now what we need to do is simply to perform a binary OR with the value hex 0004. This is a 16-bit value where only bit 2 is set, which, remember, is the bit that we want to set in the command register. Everything else will stay the same. Then we will call the inverse of this function. In fact, actually, we can just copy this again. That's quicker. And exchange the G for an S. Everything else can actually stay the same. It's still a PCI configuration, it's still in bus 0. Obviously, we want to write back to the same device, so the same slot number. This time we want to read from the command register. So this is now a read pointer instead of an input parameter instead of an output parameter. We still want to write to the bus at offset hex 04, and of course the size of our buffer is also still the same. Modifying the contents did not change the size. Right, that's the final thing we needed to do. And now we just need to return status success. So now that we're finished with that, how do we actually compile this into a sys file to use as a driver? Well, for that we use the DDK. So we go to Start, programs, Windows NT DDK, there are two build environments here. There's the free build environment and the checked build environment. And basically the checked build environment is like a debug build and the free build environment is like a release build. We will immediately go straight for the free build environment. To build our driver, we just run the command build, nothing else. There are other parameters, but it seems that external files are really how you are meant to configure the build tool. We'll see that shortly. So while the build tool has done a lot now, it hasn't done anything of interest to us because it can't see our source code yet. It has instead built the included sample source code files. To get it to build our driver, we need to go to C DDK and change the appropriate files. To the best of my understanding, there is a parameter to specify additional source directories, but then it's still going to build all the other stuff that we don't care about. And assuming you want to do anything more complicated, that would probably quickly get old. So, the first thing we have to change is the DIRS file. Now, the way this works is the build tool looks for the DIRS file in the root of the DDK, here, and then iterates over all the directories specified therein. For example, here it specifies source. These directories may then each contain a DIRS file of their own, which the build tool also processes. So it basically recurses throughout all directories specified in DIRS files until it finds a leaf directory without a DIRS file. Now the leaf directories would then each contain a sources file, which we will get to shortly. We will edit the DIRS file in the DDK root directory and change the line DIRS equals source to DIRS equals AC97 fix. If we would now run the build tool, it would see that DIRS contains only AC97 fix and therefore continue looking in that directory. The next thing we have to do is to use a text editor. I will be using Notepad++, to, let's just type anything, to save a new sources file into our AC97 fix directory. This file contains a few parameters, which I have based on the sample sources files included with the DDK. I am not an expert on this. Firstly, we specify the target name, which will basically be the file name portion of the sys file, so AC97 fix. Then we want the target path, which will just be lib. This will be relative to the current directory, i.e. the AC97 fix directory. More on that shortly. The target type can simply be specified as driver. Then we need to specify our includes, so where the libraries that we are going to be using are located. Well, they happen to be in the inc subdirectory of the DDK root. The most robust way to specify this is to use the basedir variable like so. $, open parenthesis, basedir, close parenthesis. So this points to wherever the DDK root is, as far as I understand it. And then, of course, we need to specify that it's in the inc subdirectory of that. Finally, we need to specify the sources parameter. This is just a list of the source code files to use. In this case, we only have ac97fix.c. Right, that's the contents of the sources file, but there is one last file we have to add. Fortunately, it's the simplest one of them all. We can just go to source, general, simple, sys. We could go to any project, and then we can copy this file, this make file. It's the same everywhere. And paste it into our AC97 fix directory. The only thing the makefile tells the compiler is not to use the makefile, or rather to instead use a common globally defined makefile. Hence why we can just copy it and why it's the same for all projects. Now these are all the files we needed to create, but there is one more quirk of the DDK, and that's if you run build, it will generate the lib subfolder that we specified in the target path variable for sources. And this is where the compiled code will be go. Yes, where the compiled code will be go. Then it will also generate an i386 subfolder, which is the default processor architecture. You could, of course, build this driver for other CPU architectures that Windows NT 4.0 supports, but we'll just do it for x86. But what the build tool will not create is the free subfolder to distinguish the output of the free build environment from the checked build environment. So you will need to create this subfolder yourself, otherwise the compiler will complain that it cannot put the sys file there. Oh, Microsoft. If we run build, it should create our AC97 fix.sys file. It looks like that worked. So now if we go into the free directory, we have AC97 fix.sys, the actual finalized binary file of our driver. Now we have the binary file of our driver, but for Windows NT 4.0 to recognize it, we also need to modify the registry. The most convenient way to do this, especially if you want to do this repeatedly and on other systems, is to create a .reg file. So we will open Notepad++, create a new file, and save it as ac97fix.reg. Every regedit file has to start with the version of regedit that it was created by or is intended for. In this case, it's the latter. But I presume it's backwards compatible. But anyways, and in this case, Windows NT 4 uses regedit 4. Fairly straightforward. Then you specify the registry keys that you want to modify or create. So in our case, we specify hkey local machine \system \current control set \services \ac97fix. Let me zoom out a bit. Firstly, we will add a type key, which has a dword value of 1. This specifies which kind of driver this is. 1 is a kernel mode driver. There are also file system drivers, for example. But we want this to be a kernel mode driver, like the actual AC97 driver. Then we want a start key, which again is has a dword value of 1. This means it is a system start driver. So it starts with the kernel, just like the actual AC97 driver. If this were 0, then it would be a boot start driver, so it would start with the bootloader, so before the kernel. Fun fact, ChatGPT actually thought the fix should be a boot start driver, so it would run before the real AC97 driver. But it turned out that the fix wouldn't work then. Evidently, something else is disabling bus mastering again after the bootloader runs. I suspect it's the OS kernel. It might also be the real AC97 drivers, I guess. But at any rate, the fix works fine as a system start driver, so we will leave it as that. The next key is error control. It is another dword, and it has another dword value of 1. And this is just the severity level of a failure to load. So 0 means only log the error, but don't bother the user about it. 1 means log the error and also show an error message, which might be quite helpful if our fix fails. Finally, arguably the most important parameter is image path. Now, this is a string, and you don't actually need to prefix that with its data type. You just open a double quote. Now, the path starts with system root. Well, first of all, it starts with a double backslash. This is just to escape the backslash, because you could put escape sequences in here. But in order for, like, backslash n for a new line, for example, or on Windows it will be backslash r backslash n. But anyways, and if you want to put an actual backslash instead of, say, an escape sequence backslash capital S, which I don't think exists, if you want to put a literal backslash, you just have to escape the backslash with another backslash. And now system root is a variable that usually points to cwinnt, but if you install Windows NT to a different location, C Windows, for example, then system root would contain the actual file path of the, well, system root, hence why it's called that. So this, of course, makes the driver much more robust when running on different Windows NT 4.0 installations. Now then, so system root normally points to cwinnt, and then we need to follow the path system32, drivers, and finally the file that we want to access is ac97fix.sys. You will probably recognize this from when we installed the driver for PCI tree earlier. Oh, and of course we need the closing quote. Now that we've written the regedit file, we can just double-click and run it. That was successful, at least it claims to have been successful. We can verify this by running regedit and going to the key we just created, hkey local machine, system, current control set, services, and there is AC97fix, and if we look here, error control is 1, start is 1, type is 1, and image path is system root, system32, drivers, AC97fix. Interestingly enough, I guess the parser, I guess it's only for the parser that you have to escape the backslashes. In the actual registry, it has the expected output. Finally, we just need to copy our .sys file to the image path we've just specified. So to cwinnt system32 drivers. We are now ready to test our driver by restarting. But before we can do this, we need to temporarily disable the Windows shutdown sound. Otherwise, because the real AC97 driver is currently half working, Windows will wait for the shutdown sound to finish playing before actually shutting down. But the sound will not play yet because the driver isn't actually able to output it yet, and so Windows will get stuck waiting forever for a sound that never plays. So we go to the control panel, sounds, find the exit Windows sound, and set it to none for now. We can, of course, re-enable it once we know that sound is working. Now for the moment of truth. We will restart the system, and if we've done everything right, we should hear the startup sound on the next boot up. If we've done everything right, when I click OK here to log in, we should hear the Windows NT 4.0 startup sound. So there we go, working audio from boot up. If we go into PCI tree and examine the command register, we see that bit 2 is now already set, where previously it was cleared after boot up. So now we have our own helper driver that lets us use an AC97 driver intended for another controller in VirtualBox. There is still some hiss to the audio, but at this point that does not seem to have to do with the sound driver anymore, but rather the low bitrate of the audio files themselves. Apparently the bitrate was lowered during Windows NT 4.0's development for some reason. At any rate, at least the distortion that you hear on SoundBlaster 16 emulation is gone. The source code and a ready-made compiled version of this helper driver are available on GitLab. I will link any resources used in this video, such as PCI tree or the VIA audio driver, in the video description. I hope this wasn't too confusing and that you found this interesting. And if you have any criticisms, corrections, or would like to share something about Windows NT driver development, I would very much welcome that. But that's it for this video. Good night!